Okay, so we will consider an enclosure composed of two surfaces. And these surfaces are at different temperatures from each other. So surface 2, which has a certain area, temperature, and emissivity, and surface 1. And then there's going to be some net radiation exchange just between the two surfaces. And because there are only two surfaces here, we can say that the net radiation from surface 1 is going to equal the net radiation to surface 2, and that's going to equal the net radiation exchange between the two surfaces. So it's simplified for this case of just two surfaces. So that lets us say that Q1, the total net radiation leaving surface 1, is equal to negative Q sub 2. So the net radiation to surface 2. And it's negative because we're assuming that Q sub 1 is the net radiation from a surface. So negative Q sub 2 is going to be the net radiation to that surface. And that's equal to the net radiation exchange between just the two surfaces. Okay, so we can draw our radiation networks for these two surfaces separately. So let's go back and look at the big network schematic for a second. So here we have whichever surface we're considering, surface I, going to surfaces 1 through N. And when you write the radiation network for each of the surfaces individually, say we're starting with surface 1, 1 would be I, and then we basically start with 2 and go through N. So even though the view factor for a surface to itself, F11 for example, could be non-zero because our surface can see itself, there will be no net radiation exchange between a surface and itself because it's isothermal, basically. So even though the view factor could be non-zero, you won't have any net radiation exchange between that surface and itself because it's at the same temperature as itself. So that's why we'll have basically one fewer summation on the right-hand side than we have number of surfaces for each surface we consider. Okay, so let's write that out for surface 1 first. So we have the first node is the emissive power of the surface if it was a black body. And then we have some resistance. Because the surface is not a black body, it will emit at a lower power. And then the radiosity, J sub 1, of the surface under consideration. And then the radiosity of the other surface, or the second surface that we're considering, which in this case is the only other surface. And again, there's some resistance between the radiation exchange between these two surfaces just due to the V factor. And this will be Q1 to 2. And then over here we'll have also Q1. And then if we consider now surface 2 is our surface of interest. So we're saying, okay, what's the net heat transfer from surface 2? Now the first node is EB2. And then J sub 2. J sub 1. And then that's the net radiation exchange between surfaces 2 and 1. And then we have the resistances. And then from our reciprocity relation with the view factors, we can say that this resistance is equal to A1F12. Any questions about how that's set up? So for more surfaces, you would just keep adding basically more circuits for each different surface. And for more surfaces, you would also have, basically this would branch into a set of parallel circuits where you had surface 2, 3, 4, 5, 6, etc. So we can simplify this because it's just two surfaces and rewrite the total thermal resistance . So now we can say the total resistance to net radiation exchange between the two surfaces So we can now write this as one circuit. So starting with surface 1, the emissive power, if it were a black body, radiosity of surface 1, radiosity of surface 2, and then over to the emissive power of surface 2. With the respective resistances in there. So we can write the total resistance like this because Q sub 1 is directly equal to negative Q sub 2. And if you look back at the original circuits, you can see that they're still kind of represented accurately in this circuit. So one of the things about the total resistance concept that is really useful is, given this entire total resistance, the heat transfer rate between each of the two, or each section, is the same. So that's kind of the concept that we first developed when we introduced this. So you can take the total difference between any of these two nodes that are in line and divide it by the total resistance between those two nodes, and that's still equal to the heat transfer rate. So if you look at surface 1, that circuit is represented here. And so if you just take this section, that's still going to have that same Q sub 1 rate of heat transfer going through it. And the same thing with the surface 2. Basically, that's represented right here. And because it's flipped, now we're showing that it's negative Q sub 2. So it's still consistent with the original circuits that we wrote down, but because it's just two surfaces, we can write it as the total resistance here. Okay, so now we're going to write this in equation form. And because it's much easier to calculate the emissive power of black bodies than radiosity, we're going to use those nodes as kind of the endpoints for the numerator. And then our total resistance on the bottom. And then we know the expression for the emissive power of a black body. It's just sigma times the temperature to the fourth. So we can plug that into the numerator. So sigma times T sub 1 to the fourth minus T sub 2 to the fourth. Over the total resistance. And this is kind of our general equation for radiation exchange between two surfaces. That form an enclosure. And are isothermal, so each surface is individually isothermal, diffuse, and gray. And then last requirement with uniform radiosity and irradiation. And lots of surfaces at least approximately meet this criteria. Okay, does that make sense, how we got there? Okay, so the last thing we're going to do is we're going to consider a special case of this two-surface enclosure. And that's a small convex object in a large isothermal cavity or large isothermal surroundings. So you should recognize these are the conditions that we first talked about when we were introducing radiation. And we use this equation for your second lab. So if you think you had the sphere hanging from the stand, small convex object, in large, generally isothermal surroundings of the room. So we have surroundings, we have a small object, The object has a certain surface area, temperature, emissivity, and the surroundings, which are surface 2, have a different area, temperature, and emissivity. We're going to say that A sub 2 is much, much larger than A sub 1. So A sub 2 approximates a black body. So just based on the size of the relative size of the two surfaces, A sub 2 is much more likely to absorb all of the, or almost all of the radiation in the room. So therefore, we can say that the emissivity, E sub 2, or epsilon sub 2, is equal to 1. So this surface is approximately a black body, so its emissivity will be 1. And from looking at the setup, we can just tell that the view factor, f1 to 2, is going to be 1. So this is a convex object. So from the summation rule, f11 plus f12 equals 1. f11 will be 0. f12 is 1. So now if we go back and look at our original equation up here, and we'll rewrite this given these simplifications. So epsilon sub 2 goes to 1, so this entire term goes to 0, and then f12 is 1. So you're just left with this expression. Whoops. There we go. So this term goes to 0, and this term goes to 1. We can simplify this a little further. Basically, if we bring these two together in the denominator, these cancel. And then we recover this equation. So this is equivalent to a familiar equation where we said T sub 1 was the surface and T sub 2 was the surroundings. That we started off with when we first introduced radiation. So this is net radiation from the surface to the surroundings. So we can write down kind of the restrictions of this equation right here next to it. So this applies to a small convex object in large isothermal surroundings. where the object is also individually isothermal. The surfaces are opaque, diffuse, and gray. With uniform radiosity and irradiation. Okay, any questions? So now we've kind of formally derived this equation, shown exactly where it's applicable, and it's very convenient to be able to apply it even if it's only approximately applicable in some cases. Okay, that's it. Any questions? All right. Okay, so again, thanks for coming on the last day. We're going to do the course evaluation now. First, I want to give a quick quarter in review, just to remind you all everything that we've gone over. So we started with conduction. Started with the physical mechanisms that drive heat transfer. And then we talked about conduction and figured out how to calculate the rate of heat transfer via conduction through plane walls and also cylinders. So Cartesian and cylindrical coordinates. And then how to calculate the temperature distribution within those objects as well. And then we moved on to extended surfaces with lots of different boundary conditions and how to calculate the heat transfer rate from those and the temperature distribution along the surfaces. And then transient conduction, specifically just the lumped capacitance method. And we had, for those, we basically introduced convection just as a boundary condition initially, where we had a simple rate equation for it, and we were kind of just given all of the values that go into the convection equation, or solve for them experimentally, like in the lab. And then we talked about boundary layer development and learned how that influenced convection, and figured out how to actually calculate those values of H that go into the convection equation, and how to calculate those for lots of different geometries, different flow conditions for internal flow and external flow. And then took those concepts and applied them to heat exchangers. So we talked about concentric tube heat exchangers, parallel and counterflow configurations, and how to calculate the heat transfer rate in the heat exchanger. And then finally, went over properties of radiation, how to calculate radiation exchange between two surfaces and between surfaces in an enclosure for both blackbody surfaces and real surfaces. And touched on material or covered material in 10 chapters in 10 weeks, so not too bad. I would say good work on all's part. I appreciated all your effort this quarter. So we got through quite a lot. So last thing, aside from Monday, is I have lots of forms for you all. So we have evaluations for